All right, we're back. We're on page 4 of note 6. And it looks kind of like mixed review, I guess. We're going to do these in whatever we think is the best possible way. So let's get started. So I look at A and I think I would like to do limit comparison on this because this basically to me looks like 1 over n squared, right? It's n over n cubed. So what I'm going to do is I'm going to compare this to 1 over n squared. So basically what you do, you look at the dominant term there, simplify it, get rid of a constant multiple, and then if you know what's happening here, so this is convergent, p equals 2, which is greater than 1. If we know what happens with that, we know what happens with the other one, basically. So let's see, limit as n approaches infinity. So the original series is this. I'm going to compare it to 1 over n squared, but I'll invert that right away. Get the limit as n approaches infinity of 2n cubed over n cubed plus 1, which is 2. That's positive and finite. So since the sum of 1 over n squared converges, p equals 2, we know that this series converges too. There's really not, I think, enough room to do all these, but that's okay. Well, is that okay? I don't know. Converges by, maybe some of them will be easier or less space. It won't really matter. It's not like you can borrow the space from one problem for another. But I guess you can. I don't know. Like I'll take this and move it over a little bit so that it's not in the way, so that the other one has more room, I guess. I don't know. All right, this one looks, I don't know. This looks challenging. I mean, it doesn't. What do we know? We know geometric. This is definitely not geometric. We know telescoping, which there's no way this telescopes. We know the n-term test for divergence, but I'm pretty sure that this goes to 0 if you take the limit. So the integral test is really tempting, except I don't think I would be able to find the integral, but I think the calculator would, and the calculator can find the derivative and all that. It's definitely not a p-series. I don't really know what I'm going to direct compare it to. I guess you could compare it to n. So 1, okay, I'm starting to have an idea here. I'm going to try this. I'm going to try the integral test. No, I have an idea. I have ideas, people. So I think the calculator could just do the integral test on this, and I think that'd probably be the best thing. But let me start off with looking at just n over e to the n squared, right? Or actually, it's probably easier to deal with if I leave it the way it's written. I'm going to look at the numerator. So we get this, right? So that's, if we say f of x is x e to the negative x squared, that's definitely positive and definitely decreasing. Positive, it is continuous. It's decreasing eventually. I don't know if it's decreasing initially, but like, let's take liberties with that. Let's just say decreasing. The integral from 1 to infinity of x e to the negative x squared is going to be the limit as b approaches infinity of 1 to b x e to the negative x squared, which is the limit as b approaches infinity. So the antiderivative, you'd need -2, -1/2. I'm going to get -2 over e to the x squared from 1 to b, which equals, all right, so you sub in b and you take the limit and that goes away. So it's minus -1/2. So I'm going to say 1/2. Therefore, this converges, no, 1 over 2e. 1 over 2. See, you get a little cavalier and bites you immediately. So we get this. Therefore, I'm just going to say therefore the series converges to save myself like 600 years. So why is this helpful? All right, by integral test. So I use the integral test there. So now I know that ne to the negative n squared converges. So that's useful, sort of, because 1 over 4 plus e to the negative, okay. So what I need in the middle of doing an annoying problem is I need it to auto format things for me. So what does this become? This is e to the n over 4 e to the n minus 1. This is less than 1 for, I don't know, for n values. I think actually for all n, but it's basically 1/4. So that's less than 1. So why is that useful? That's useful because it means that if I take this thing and multiply it by this, so if I take this, well, take the whole thing actually. I'm going to take all of this and multiply it by this. So that'll give me ne to the negative n squared over 4 plus e to the negative n is less than ne to the negative n squared. So I don't know if you're completely following what I'm doing. I'm going to try to use direct comparison, which I think at this point is good to go. So the key there were like 2 key observations. There were more than 2 key observations. The main key observation, I would say, is that you could have just used the integral test on this with a calculator, and the calculator would do all the work, and you would get converges by the integral test. What I decided to do was I decided to take the numerator and do the integral test on it, and then because I now know that that series converges, do direct comparison. And it only works because of this little bit right here. This is what's making that work. So since this thing in the middle in particular is less than 1, and it's easy to see that that's less than 1, we can do this. So I'm going to say, okay, so since the sum of ne to the negative n squared converges by integral test, the sum of ne to the negative n squared divided by something, 4 plus e to the negative n, converges by direct comparison. So that was a doozy. Also, I think I should say therefore. Since that, no, I don't need that. So since that's true. All right, whew. So you might want to take a look at that one again. I think definitely. You should definitely take another look at that. All right, let's do dominant terms. All right, dominant terms. What's dominant? Well, n squared dominates. This dominates. So I'm going to compare it to n squared divided by n to the 5/2, which is, not loving these summation signs. 1 over n to the 1/2, which definitely diverges because p is 1/2. All right, so I know this thing definitely diverges. That you're basically done. So we do the limit as n approaches infinity, 2n squared n to the 5/2 plus 2 times n to the 1/2 over 1 is the limit as n approaches. So I'm always inverting that the bottom of the fraction of the ratio, whatever you want to call it, because it just like skips I think sort of unnecessary step. The assumption being that you kind of know what you're doing. Positive, finite. But I always think like, why are you taking this if you don't know what you're doing with these things? Like go back and review, get really good at that, and then come back. Don't rush into this. There's no point in that. Positive, finite. All right, so they do the same thing. So since 1 over n to the 1/2 diverges with p equals 1/2. The given thing also diverges, and that is 2n squared over n to the 5/2 plus 2 diverges by limit comparison test. many are there? Let's see. Should I make a second video? Oh my God, I should definitely make a second video. All right, I'll do one more here and then come back. I didn't realize there were like 1,000. I'm just going to compare to 1 over n, which I know diverges. It's the harmonic series. So limit as n approaches infinity. You know what? I'm going to skip a bunch of steps. I'm going to do the multiplication also. You get n to the 5th plus 2n squared minus n to the 5th plus 3n squared. It's almost like you almost feel bad over time for the non-dominant terms because they don't do anything. You just end up disregarding them. Positive finite. So since 1 over n diverges, I'm going to say it's harmonic. You could say it's p equals 1, which is easier to spell than harmonic. We know that n to the 4th plus 2n minus 1 over n to the 5th plus 3n squared plus 1 diverges by limit comparison. So I'll use limit comparison all day if it applies, which it like usually does. All right, I'm gonna stop there and come back in the next one and do more of these. I don't even know if I'll finish in the next video. Who knows? All right, so hopefully I will see you there if you're looking for more practice. Yeah, see you.